Hi everyone, it's Japoo, and today we're going to be talking about areas. Before I get started, I wanted to remind you guys that the worksheet that I'm about to do and its answer key are linked in the description below, so check that out if you would like to follow along. So first, I'm just going to talk about how to approach these area problems. Usually you're trying to find a region or the area of a region in between two functions. So the formula that I like to follow is top minus bottom. Here I'm dealing with the vertical distance between the two functions to help me find the area. So everything that I'm doing would be in x's. This will make a lot more sense when we get to actually drawing the graphs out, but the top and the bottom are going to refer to the top and bottom of a rectangle that I'll draw between the two functions that are enclosing the area that I'm trying to find. Sometimes the function is sideways, so instead of doing top minus bottom, we're going to do right minus left. And as you can see, it's right minus left times dy. So everything in that equation, when I'm dealing with right minus left, will be in y's. And I'll show an example of that in this worksheet. So let's go ahead and start with number 1. The first thing that I want to do is draw a graph if I'm not provided a graph. Your graph doesn't have to be 100% perfect. You're just going to try and represent the area that you're looking to find. So in this problem, we're finding the area of a region enclosed by the graph y equals e to the negative x, the vertical line x equals -1 and x equals -2 and the x-axis. So I'm going to go ahead and draw that. So there's my -1, 1, and 2 on the axis, and that's my e to the negative x. So since we know that the area enclosed by the region is kind of in between e to the negative x and the x-axis, that's going to be the two functions that are enclosing my region. And as you can see, I drew a rectangle in between those two functions. The rectangle represents the vertical distance, so the top of the rectangle will be the top in my equation, and the bottom of the rectangle will be my bottom in this equation. When I say the top of the rectangle, I really mean what the top of the rectangle is touching. Which function is the top of the rectangle touching, and which function is the bottom of the rectangle touching? So then we will go ahead and kind of write our formula. So we know that the area is enclosed by 2 and -1, so those are going to be our parameters on our integral. And then we're going to have our top, which we know is e to the negative x, because that's the top function in this case. And then we're going to subtract that by the bottom, which is just 0, because it's just the x-axis, times dx. Now, in order to find the integral of e to the negative x, we do have to do a u-sub. You should definitely watch our video on definite u-subs if you're a little confused by this process. But basically what we're going to do is set negative x equal to u. So then we would take the derivative of u to get du, and that gives us negative dx, right? And then we kind of want to isolate dx so we can replace it with du, and as you can see, we get a negative du. So then we're also going to want to replace the parameters that are in terms of x's and make them in terms of u's. So x equals -1, we plug that into u, so we get u equals -1, which is just +1. So then x equals 2 would equal u equals -2. So now that we have those parameters, we can go ahead and make our new integral. So we're going to have a 1 on the bottom and a -2 on the top. And then e to the u times du. And make sure you put that negative in front of the integral because dx is equal to -du. Then we're just going to take the antiderivative of e to the u, and that is just e to the u, and we bring over that negative that was in front of the integral, and then plug in -2 and 1. And this is just FTC. So then our final answer is going to be -1 over e squared plus e, and that is the area of region R. All right, so let's try another problem. That one was fairly straightforward, especially because one of our functions that was enclosing our area was just the x-axis. So the bottom of our rectangle, the function at the bottom of our rectangle was equal to 0. For this next one, you can see that we are given two functions. We're given f and g. F is equal to -x squared plus 3, and g is equal to x plus 1. So again, we're going to draw a graph since it isn't provided to us. Again, the graphs aren't super important. You really just need to identify which is the top function and which is the bottom function. If you flip the functions by accident, you will get a negative answer. So you just need to negate your answer to get the positive version of that answer, because area always has to be positive. We're not finding negative areas. But if we draw our functions correctly, we're going to get f looking something like this, and our g will look something like this. Oh, sorry, that was still f. Our g is going to look like a diagonal line right below that f function. So that's our g right there. So then that space in between f and g is going to be the region R, which we're finding the area of. And I'm going to go ahead and draw my rectangle dx right there. And that's just going to help me find the top function and the bottom function and make sure that I don't mix them up. Now we're going to find our intersection points. To find our intersection points, we basically just set the f graph or the f equation equal to the g equation, just to find out what these points are, what the values of these points are. We need to find those values for the parameters for our integral. So I'm going to set -x squared plus 3 equal to x plus 1. And that's going to give me x squared plus x minus 2 equals 0. And if I factor that, I'm going to get x minus 1 times x plus 2, which means that x is equal to 1 and x is equal to -2 when these two graphs, f and g, intersect. So now that I have my intersection points, I can go ahead and write my integral to solve for my area. So area is going to equal integral, and then 1 and -2 will be my parameters for that. And then I'm going to have top minus bottom in this case, according to my rectangle. The top function is going to be the f function, since the top of the rectangle is touching the f function. The f function is -x squared plus 3. And I'm going to put that in parentheses to make sure that I'm not accidentally subtracting something when I'm supposed to be adding something, and making sure that my top quantity and my bottom quantity are properly separated before I try and combine them or take the integral or whatever I decide to do. So we're going to subtract that by our bottom function, which is the g function, since the bottom of the rectangle is touching g. And that's going to be x plus 1. And then we're going to put dx, of course. I'm actually going to go ahead and simplify that equation inside the integral. So again, keeping the same parameters, I'm going to have negative x squared minus x plus 2 times dx. And then I'm just going to take the integral of that. So the integral of negative x squared minus x plus 2 is going to be negative x cubed over 3 minus x squared over 2 plus 2x. And that's just the simple power rule when dealing with integrals or taking antiderivatives. And then I'm just going to go ahead and plug in 1 and negative 2. So I'm going to get negative 1/3 minus 1/2 plus 2, all of that in parentheses, minus 8 over 3 minus 2 minus 4. And that's also in parentheses. And that's all going to be equal to 9/2. So the area of the region in between function f and function g is going to equal 9/2. Okay, let's move on to number 3. So in number 3, we're actually given the graph, so we don't have to draw it, thank God, because I really don't like drawing trig graphs. But we know what region of the graph we're trying to find the area of. It's the shaded region. So the first thing I'm going to do is just go ahead and I'm going to draw that rectangle. And that rectangle is going to help me obviously determine which function is going to be my top function and which function is going to be my bottom function. So once I do that, I'm just going to jump right in and start my area. So I know that my parameters for this integral are going to be 1/2 and 0 because 0 is this kind of like edge of the area, and then we can see that the two functions intersect at 0.5 right here. So that's the other edge of the area. So my top function is going to be cosine pi x. So I'm going to write cosine pi x. And I'm going to go ahead and subtract that by the bottom function, which is x minus 1. To take the integral of cosine pi x, we're going to have to do a u sub. So u is going to be equal to pi x, which means that du is going to be equal to pi times dx. When we isolate dx, we're going to get 1 over pi times du. So remember to put that 1 over pi in front of the integral. And then our top is going to become cosine u times du. And then we're going to keep the x minus 1 integral separate because we don't have to change the parameters from that for the integral, right? We don't have to change 1/2 and 0 for x minus 1 because we're still dealing with x's in that integral. However, with the cosine u integral, we're dealing with u's now. So we have to change our x values to u values for that integral, which is why we have to separate those two quantities. So when x equals 0, u will equal 0 because 0 times pi is 0. We're plugging that back into u. And if we plug in 1/2 into the u equation, pi times 1/2 is pi over 2. So our new values for our cosine u integral are going to be 0 and pi over 2. Now we're going to go ahead and take the antiderivative of both of those integrals. So the antiderivative of cosine u is going to be sine u, and we're going to go ahead and bring over that 1 pi also that was in front of that cosine u integral. So we're going to have 1 pi times sine u. And we know that we're going to plug in pi over 2 and 0 for u. Then we're going to take the antiderivative of the x minus 1 integral, which is going to give us negative x squared over 2 minus 2. And we're going to plug in 1/2 and x equals 0 there. So that's going to give us 1 over pi minus, in parentheses, 1 over 8 minus 1 over 2, when we eventually plug all those values in, which can be simplified to 1 over pi plus 3 over 8. So that's going to be our area for this shaded region for number 3. Moving on, we're going to head on to number 4. Let me move this. Okay. So number 4, I'm going to have to draw my graph since I was not given a graph. We know that the region is going to be enclosed by x plus y squared equals 2, and the vertical line x minus 1. So in this case, if we do, we would normally try and draw a vertical rectangle, right? However, if we tried to draw a vertical rectangle in our shaded region, we'd find that we would have a top and bottom that are the same function. So in this case, we actually have to do a horizontal rectangle so we can follow the equation area equals the integral of right minus left. So that's why I decided to go ahead and rewrite this x plus y squared equals 2 equation in terms of y's, because I know that I'm going to be dealing with an equation where I subtract the right function, where I subtract the left function from the right function since it's right minus left, and therefore I'm dealing with y's. So first we're going to find our intersection point. After, I'm just going to label this graph. So we can kind of see that the right function is going to be, or sorry, the left function is going to be x equals 1 right here. And the right function is going to be x equals negative y squared plus 3 right here. Because that's where the right and the left sides of our rectangle are touching. Okay, now intersection points. So what we're going to do is set both of our functions equal to each other. So we're going to have 1 equals negative y squared plus 2, which we can kind of rewrite to be y squared equals 1, which means that y is equal to plus or minus 1. So the actual coordinates, like the xy coordinates where the two functions intersect, are going to be 1 comma negative 1 and 1 comma positive 1. But since we're only dealing with y's in this equation, we only need the y coordinates for our integral. So our area is going to be equal to an integral with negative 1 on the bottom and 1 on the top. And then we're going to have right, which is this kind of sideways parabola looking function, negative y squared plus 2 minus 1, which is the vertical line, times dy. So that's right minus left in this case, because if we try to do top minus bottom, we'd get the same function for the top function as we would for the bottom function, which would not give us an area. So we're going to take the antiderivative of that, and we're going to get negative y cubed over 3 plus y. And we're going to plug in 1 and negative 1. Once we do that, we are going to get negative 1/3 plus 1 in parentheses minus 1/3 minus 1. And that's just going to go ahead and give us an area equal to 4/3. So this shaded region right here is going to be equal to 4/3. And now we're going to go ahead and start on the second page. So a lot of the times, these kinds of area questions are calculator-friendly questions. So you can do the integral or find the antiderivative or whatever in your calculator. However, you can still make mistakes in these problems. Sometimes when you're typing the problem into your calculator, you could type it in wrong, which will give you the incorrect answer. And I know, at least for me, I always feel more comfortable typing my answer into the calculator, so I often don't double check myself as much when I'm doing these problems. But it's really make sure to double check yourself and make sure that you have typed the problem correctly into the calculator. It's really easy to mistype these problems. For example, instead of typing in the top equation minus the bottom equation, you might switch it up and accidentally type in the bottom minus the top equation, and that could really mess up your answer. But anyway, let's get started on this first question. We have an area, or we have a region R, that's the shaded region, and we're trying to find the area of that. We have two graphs, ln of x squared and x squared minus 3x plus 2. So luckily for us, our graph is labeled. We see that f is this graph right here, and g is this one right here. And if we go ahead and draw our rectangle, we notice that the top equation in this case is going to be the f, and the bottom is going to be the g. Once we have that, we can go ahead and write our integral. We know that our parameters for this integral are going to be 1 and 2, because we can see that our intersection point is labeled right here as 1, and the region is enclosed by vertical line x equals 2. We can also see this where the shaded region stops. So we're going to essentially have an equation that's the area equals integral from 1 to 2, f of x minus g of x times dx. And if we write down the actual equation and replace that with replace the f of x and g of x with the actual equations, this is what we're going to get. And what I want you guys to do is plug this exact integral into your equation. And don't forget to use parentheses. Even if it seems like you're putting way too many parentheses, that's fine, because you want to make sure that you separate the top and the bottom. And so however you want to do that in your calculator with your parentheses, just make sure you do that. I really recommend like this exact equation, like with parentheses and everything, is a perfect thing to type into your calculator. If you type this exactly in, you're going to get the correct answer. But again, making sure that you type your equation correctly into your calculator is key. But if you type this incorrectly, then you're going to get 0.939 as your answer. So the area of the shaded region is 0.939. On number 6, we are not given a graph. I elected to just go ahead and draw the graph on my piece of paper, But since you can use a calculator in this in these problems, you can just go ahead and graph this these two functions on your calculator if you have a graphing calculator. So the area, the region R, which we're trying to find the area, is enclosed by the graph f of x equals x squared plus 4 and the horizontal line y equals 7. So as you can see, up here is my horizontal line y equals 7, and here is my parabola that represents x squared plus 4. Now we do still need to find our intersection points for this integral since we're not given them in the problem. And when I have these calculator-friendly problems dealing with area, I like to find these intersection points in my graph, or in my calculator, sorry. And I do that by graphing the two equations and finding where they intersect. I would recommend not using the solve button if you have that function in your calculator, but actually graphing the two functions and finding the points where they intersect. Technically, you don't need the y-coordinate, even though I wrote it here, of the two intersection points. But sometimes on free response questions on the AP exam or college exams, you may need the y-coordinate for part of the problem, so it's good to just have them. But again, I found these two intersection points by graphing the two graphs, or the two-leg equations, the y equals 7 and the x squared plus 4, into my calculator. Once I do that, I can go ahead and find the area of the shaded region. So my two points on my integral are going to be negative square root of 3 and positive square root of 3, based on my intersection points, the x coordinates of my intersection points. And I'm going to have 7 minus x squared plus 4. Because y equals 7 is my top function, and x squared plus 4 is my bottom function. That's going to give me 4 square root of 3, which is equal to 6.928. Again, I typed this into my calculator, and I made sure to watch my parentheses when I typed it into my calculator to make sure that I got the correct answer. So moving on to number 7. Number 7 is a little trickier because the top and bottom functions actually change in the middle of this function, so we do have to do two separate integrals. So I only drew one rectangle where I decided that like the square root of x is my top function right here, and the y-axis is my bottom function. But if I drew a rectangle right here in this area, I'd have 3 minus x as my top function, and then my bottom function would continue to be the x-axis. But since we have two different top functions, we do have to go ahead and have two integrals. So, okay, so there are my two rectangles. So I'm going to find that intersection point where square root of x and 3 minus x intersect, because I know that the entire shaded region is bounded by 0 right here and 3. So I just need to find where to split the integral. So again, I'm going to go ahead and graph these two equations in my calculator and then find the intersection point via that graph. And I'm going to get 1.6772, comma 1.3028. So the x-coordinate that I will be using as my parameter for my integrals is going to be 1.6772. So we're going to go ahead and find the area. We're going to have area equals 0 and then 1.6772, because first we're going to find the area of this half of the graph up to this intersection point, right? Everywhere where the graph of square root x, or the equation square root x, is the top function for the region. So square root of x minus 0 times dx is our first integral. Our second integral is going to be from this intersection point right here to 3. So we're going to have 1.6772 to 3, and that's going to be our second integral. And from this intersection point to 3, we see that 3 minus x is our top function, since the top of the second rectangle touches the function 3 minus x. So when we plug that into our calculator, we're going to get 2.323. And this x right here should be a 0, because again, the bottom of our rectangle in our second rectangle is still the x-axis, so it should still be 0. I don't know why it's x. That was a mistake. So make sure that you know it's 0. Number 8, again, we do have a situation where the top and bottom functions change. So again, we're going to need two separate integrals. I only drew the rectangle for the second integral for some reason, but there should be, if you want to, you can draw a rectangle right here to help you figure out the top and bottom functions for the first integral. Luckily, they gave us our intersection points. Luckily they gave us our intersection points in this problem. We see that where the lines kind of cross over is 1, 1. So we don't have to graph this in our calculator to find it. Now we're going to go ahead and write what our area equation is going to look like. So for the first kind of like triangle thing, the leftmost section of the graph, I guess, the leftmost shaded region, we're going to define our integral from 0, x equals 0, which is this axis right here, to 1, right? And our top function is going to be f, and our bottom function is going to be g. So we're going to have f of x minus g of x. And then our second integral is going to be from this intersection point 1 all the way to 2, where the shaded region ends. You can see right there. It also says in the problem that the region R is bounded by a vertical line 2. So then you're going to have g of x minus f of x, since, as you can see with this little rectangle right here, the top function is going to be this g function, and the bottom function is this f function. If you, well, first of all, let me say that since they gave us the f and g functions in the problem, since they defined them in the problem, we can just write it on the paper like this. We can keep it in terms of f's and g's, because the grader will know what you mean when you say f of x and g of x, since those values were given in the problem. However, when you're typing it into your calculator, make sure to type in the actual functions. So when you're trying to type this into your calculator, for example, for the first integral, you don't want to type in f of x because your calculator doesn't know what f of x means. You want to type in 2 to the negative x squared plus x minus, and then instead of typing in g of x, you're going to type in negative x squared plus 4x minus 2. The same thing goes for the other integral. And once you do that, you should get an answer of 2.518. So the area of this region is 2.518. So let's move on to our last problem, number 9. Number 9 is a little bit different from the rest of these problems. It is a theoretical question, but once you understand what they're asking, you do the same process for every single question that looks like this. So let's look at the question in general. First, the question defines what R is. It is the shaded area right here. And then it goes on to say that the vertical line y equals k divides R into 2 regions of equal area. So what does that mean? That means that there's going to be a line splitting this graph in half equally. So the thing that I like to do is just go ahead and kind of draw this line. It doesn't have to be perfect, but it has to look kind of somewhere in the middle, just to help you. And you're going to label that line y equals k, as it says in the problem. So that's your vertical line that divides R into that's your vertical line that divides R into 2 regions of equal area. Now we're going to label those 2 regions. We're going to have region A and region B. And what we know is that the area of A has to equal the area of B. Since the line that we drew is dividing 2 regions of equal area. So the area of A is equal to the area of B. Then we're going to go ahead and kind of try to set up an equation. So we're going to use x's in this case to kind of divide up our area. And so we see in area, our region A, I guess, f is the top function and g is the bottom function, right? So everywhere before the vertical line k, from x equals 0 to x equals k, f is on the top and g is on the bottom. So for all of area A, f is the top function and g is the bottom function. And now we have to find the area of B, which we know is equal to the area of A. So lucky for us, we're given the intersection point right here of these 2 functions. And we see that the intersection point is 1.5, 1.25. Again, we're dealing with x's. So everywhere from x equals k to x equals 1.5 is region B. So those are going to be on our integral. Our integral is going to be from k to 1.5 for area B. In area B, again, f is our top function and g is our bottom function, right? So that's what we're going to write for our area B. And that's actually it. That's the answer. The problem itself says do not solve. So all you have to do is write an equation involving integrals. And if you did have to solve for this, you would be solving for k, right? So you would be able to get the value of k as a solution in this equation. So that's actually all that we have to write. Again, I'm just going to kind of recap what we did in this problem because it is a little confusing since it's different from all of the other problems. It is a more theoretical problem. You don't really have to do any math here. You just kind of have to think about it and understand what the question is asking you. The first thing that you want to do is make two separate areas of the total area that you're given, and then kind of label these regions. So in this case, I labeled them A and B. You can really choose any names that you want, but A and B is probably the easiest. After you make two areas and set them equal to each other, as I did in this first line right here, you want to do the top minus bottom of both of those areas and set them equal to each other. And that's what we did, and that was our answer. So that's really it for this video. It's fairly simple. If it helped you in any way, please go ahead and give it a like and subscribe to our channel for more videos like these. Thanks.